Okay, so far I've just told you about this idea of 95% confidence intervals, and then I've shown you a bunch of them in StatKey. But if you had the sampling distribution, how would you make it so that the statistic plus or minus the margin of error captured the parameter for 95% of samples? In other words, how would you figure out this margin of error? And as a hint, I'll say think about the 95% rule from chapter 2. So let me draw you a vaguely symmetric bell-shaped distribution, and let's say that it's centered around here. The 95% rule says that we can kind of say that 95% of the data is going to be between plus or minus 2 standard deviations. So this is x bar minus 2s, there's minus 1s, here's plus 1s, x bar plus 2s. So that indicates that our margin of error is going to be maybe 2 times the standard deviation. And in fact, that's how we're going to start making confidence intervals. If your sampling distribution is symmetric and bell-shaped, then we can estimate our 95% confidence interval, like the statistic, plus or minus 2 times the standard error. And remember, standard error is the standard deviation of the sampling distribution. So before I had an example about the proportion of all US adults who have used Instagram. Now let's think just about young adults. So Pew Research defines that as people who are 18 to 29 years old. And among young adults, 75% of them reported using Instagram. And the standard error was 3.7 percentage points. So this is the standard error, not the margin of error. And so now we have to think about how could we make a 95% confidence interval for the true proportion of young adults who have used Instagram. So we're going to have the statistic plus or minus 2 times the standard error. In this case, our statistic is p hat. And let's see, what is p hat? That's our best point estimate, 0.75. Plus or minus 2 times the standard error, 0.037. So that's 0.75 plus or minus 0.074. And that turns out to be 0.676 to 0.824. So now we want to think about interpreting confidence intervals. This is a place where intuition sometimes fails us. Statisticians are really picky about the words that you use, and it is totally okay to just use my recipe and plug in the particular words for your problem. So if we're thinking about all adults who have used an online dating site, I had found that interval to be 28 to 32%. And if I wanted to interpret that, I could say we are 95% confident that the true proportion of all adults in the US who have used an online dating site is between 28% and 32%. So you need to have something in there like 95% confident, 95% sure, and of course change that percent depending on the kind of interval you've created. If it's a 90% interval, you should say we're 90% confident. And there are a bunch of common misinterpretations. So you wouldn't want to say that 95% of the data in the population falls in that interval, because it's not about the data in the population, it's about the population parameter. We don't want to say that you're 95% sure that the proportion in a sample will fall in the interval, because when you make the interval, it's always centered on your sample statistic. And it's not true that the probability that the population parameter is in this 95% confidence interval is 0.95. The population parameter either is or isn't in this interval. We don't really have a way to know. And it's really that 95% of the time, when you generate an interval like this, that interval will contain the population parameter. But we can't say anything about this particular interval. So in synchronous class, I'd like you to think about interpreting this confidence interval about Instagram and young adults, and then we'll talk about that interpretation. Another thing that I'd like us to do in class is to create a sampling distribution that has to do with the proportion of tails. So what I'd like you to do is find a coin, ideally a quarter, but any coin will do. And we're going to come up with some sample statistics. So we know that the true probability of getting a tails is 50%, but we're going to pretend that we don't know it and we're trying to estimate it using samples. So what I want you to do is flip your coin 25 times. So you flip it once, you look, is it heads or tails, and record that. And I want you to compute your sample proportion p hat. So you're going to find p hat is equal to however many tails you get out of 25. But everyone is going to have a different number here. And then in synchronous class, we're going to build a sampling distribution of our sample proportions. I'm going to show you how to do the same thing in StatKey. So once again, I'm going to go to sampling distributions. I'm going to go to the sampling distribution for a proportion. And instead of choosing college graduates, I'm going to choose coin flip. I am interested in trying to build a sampling distribution for the proportion of tails in a coin flip. So again, we know that the true population proportion is 0.5. If we could take infinitely many coin flips, the overall proportion would be 0.5. But we're going to take samples of size 100. So we're going to have the computer flip the coin 100 times and tell us what proportion were tails. So if I click the Generate One Sample button, it takes 100 coin flips, and it says 51 of them were tails for a proportion of 0.51. If I say generate one sample again, I get another random sample. In this case, exactly 50 out of the 100 were tails. If I click generate one sample again, 52 for 52%. And so if I click the generate 100 samples button, that's going to take 100 samples of size 100. Or I could be really lazy and click the generate 1000 samples button. So this distribution is a sampling distribution for the proportion of heads. So again, I just want to highlight, I was taking samples of size 100. I took 1,103 samples. The distribution is centered around my population proportion. So it's centered around p equal to 0.5. But there's variability. Sometimes I only saw 35% tails. Sometimes I saw more than 60% tails. But I could use the 95% rule. But if I wanted to know what some other reasonable values I could have observed were, I could look at this distribution, and I could either use the 95% rule and just kind of eyeball it and say, it looks to me like 95% of the data is maybe between 0.4 and 0.6. That means that this distance is about 0.1. This is about 0.1. And so if I wanted to compute the standard deviation, I know that 2s is 0.1. Divide both sides by 2, and s is approximately equal to 0.05. So I could eyeball that from this distribution. StatKey actually is doing us one better. It's finding the standard deviation of the distribution, which is the standard error. Remember, the standard deviation of a sampling distribution is called the standard error, and it computed that the standard error was 0.051. So our estimate was pretty close. So these are some reasonable values we could have observed. So in summary, if you wanted to create a 95% confidence interval for a particular parameter, you could take a random sample from the population, compute the sample statistic, the sample proportion, the sample mean, whatever it is, write that down, and repeat those steps many times, where many is like 1,000, 10,000, many, many times. And then you're going to look at your sampling distribution, which is going to be roughly symmetric and bell-shaped, and compute the standard error by finding the standard deviation of those statistics. And then we would say the confidence interval is the statistic plus or minus 2 times the standard error. So this is how we would do it in an ideal world. But the problem is we only have one sample. We can't do step 1 1,000 times because it would be too expensive. It would take too long. So we can't actually do this, this method. So then the question is, what do we do? And that's what we'll talk about in the next section.